Greetings from Thursday, March 19, 2020. And right, my audience is here, as you can see, and there's me. So um, this is one of the first lectures through my slides that I'm preparing for Physics for Filmmakers. After our suspension was up, I had us spend a week doing part of a midterm on Canvas and part as a take-home. And the thinking there was to keep things as normal as possible. We've got to move things a little more distantly now. I'm going to keep using forums on Canvas whenever I can. And for this one, I've put up an online quiz on Canvas. It's good for participation points so you don't get anything wrong for any answers you give. Some of the multiple choice ones I expect people will make mistakes on, but I'd like you to go to the materials page for the current week, and you'll see clips from Hulk in 2001. And have you watched those? Part of the participation quiz is for you to comment on those. So watch them first, take that quiz. I'm going to discuss those quiz questions, and here I'm going to go through the slides, and it'll go more quickly because, right, when we have discussions in a real classroom, it's really cool. I plan on even hosting some time in a Zoom meeting where you can log in, maybe during regular class time, and we can continue this discussion or talk about any homework problems you're having trouble with. But this is purely the lecture part. I'm going to do a separate sample problems elsewhere involving some drawing and some math, and that's a different filming rig that I'm setting up. So I'll separate that. The way I usually do it is, well, for this lesson, actually, I break this lesson up into two pieces. If this were the normal class, then it's been the other half of class gathering data and doing tracker labs. Those are separate assignments that I've posted. And you'll see that material later, including videos, photos, anything you need to do that stuff. So even though, I spread this out over two normal lecture weeks, I can get through the purely Tim talking part now, and right, I'll do some samples, and then you should be ready to try the homework and so on. So sorry we're not all watching the clip together. Maybe through some future chat we will, but I want to at least talk through the slides here. I have a modified version, so it should show up fairly well. So let me do a screen share here. Go there. All right. So you should be seeing the slides, and I'm not doing the fancy step-by-step presentation kind of thing. That doesn't show up that well in my two monitor setup, and I'm not sure actually what gets to you. So you can see the future slides coming there, and hopefully read enough text here. I always post the slides on Canvas, so you'll be able to see that, right? So let's go through these, and again, hopefully you have had the background of having seen the clips and trying the multiple choice questions. I'll at least discuss those, and we'll get through it. So I mentioned that there's going to be a quiz next week. That's some review of exam stuff and some circular motion. I'll make that so it does count, kind of goes in that quiz setup. My initial thought is I still would like to do the final film project. I'm going to be upping a lot since this is going online. I'm going to make things like a formal final exam worth a little bit less and participation worth a little bit more, just to keep us, logging in and so on. But there will still be homework and labs, and they will be doable, hopefully at home. I'll give plenty of guidance on that. There is a new homework online as well, but just to keep with my schedule, I'm going to make that due 2 weeks probably from when you're seeing this. I'll send out separate communications about the final film project, because that one, like in a regular semester, the final film project is something that people do at home anyway. Go back and forth with me on comments and scripts and stuff like that. I hope to do enough circular motion though here, so you have a number of topics you could talk about. You saw in the sample videos that I've shown from previous classes. Many of them talk about circular motion. The other common topics I get are just regular motion, energy, collisions, that kind of thing, or come up with something that also fits under physics that you're interested in. It's really open-ended. All right. There is a section in the recommended text about where circular motion is discussed. And this is normally where I would show and talk about the clips. Again, we may do this online. I might set up a Zoom meeting for that anyway, but I'm not going to do that here. Now, the reason on that participation quiz, the reason that I asked about some vector questions is because it helps us understand some things. Now, if you've never added vectors before, there are two ways to do it. The most common way, one common way is to, if you want to add vectors A and B, you make them sides of a parallelogram, you complete the parallelogram, and then you go from here, the initial corner to the opposite corner of the parallelogram, and that tells you what's up. Another method is called tip to tail, where you just take vector A, and then from the tip of A, you put the tail of B, you have B go there, and then you make the same journey across. So the sum of these vectors A plus B is here. Now, why do I care to bring up stuff like vector addition now? Well, we've looked at and manipulated vectors before, moving in one dimension, but we usually accounted for direction with just a plus or a minus sign, and that was enough. But now that directions can change, I would like to know the change in a vector that can just change direction. Circular motion is all about that. Like you could have the same speed, but your direction is constantly changing. So that's why I asked basically these two questions, and you can see the final answers here. To subtract vectors, you can think of it like this. You take the final, whatever your final vector minus initial, right? That's the same as final plus the opposite of the initial. So subtraction is just like adding the opposite, kind of like real subtraction is. So on the quiz, right, I asked for like a down vector minus an up vector. What do you think that is? And the direction of that is up, down, or neither. I'm going to check to see how you all did on this. The most common answer I get from beginners is neither, because they say, well, it's not up or down. The answer is 0. But 0 would be the answer if that were a plus sign in the middle. If this were a plus, then down plus up is 0. You can think of it as down plus negative up, or down plus down plus down is down. So same thinking on this question. The most common wrong answer I get is A for up, but you get up if you add these, not subtract them. So if you take one vector up that way and you add the second one on, you end up up. But really, you should think about it as adding one that points down and to the right. That ends up, that gives you a total to the right. And well, why do I bring that up? If you set up a circular motion where you have an up arrow to the right and an up arrow to the left. Well, there's a way I can envision that. Maybe I could do some drawing here. I don't know. This could be an adventure. Oops. Okay. Okay, that's how I want to draw some pictures. Okay, so basic shape, something like this. Right. There's a circle. Let's suppose you move in a circle, and you think about some other well, maybe an arrow would be good. And let's say you have one arrow here and one more please. One there. All right. So these could be velocity vectors. If you're moving around this circle in a clockwise direction, at some point you have a velocity that points up and to the left, and at a later point you have a velocity that points up and to the right. All right. And if you want to find the acceleration for this question, you have to take the change in velocity divided by the time. So it's this vector minus this vector. It's that one minus that one. Okay. This minus this, to see what direction the acceleration would be. Now, adding or subtracting those two is the same as like adding these two. So you get a final answer to the right. That means along this section of the circle, if you're going in a clockwise direction, in this section of the circle, your acceleration points toward the center. And that's the basis for everything, really. Right? The direction of the change in velocity is to the right, and the acceleration is to the right. Again, that is when you're transitioning from something like that to something like this, right? You get, demonstrate again, you draw it in like that. And if I'm gonna make this a different color, or at least I'm gonna try. There we go. Okay, so the change in velocity would point toward the center, right? Which means you need a force toward the center. So most of the time when I show like that clip of the Hulk throwing the tank, right? You may have found a lot of problems with how he did that, but I would ask, what does he have to do to the barrel? Does he need to push out or pull in? And if you look at this kind of picture, that would confirm for you that you need to pull inward. And this inward pulling is what's called a centripetal force because it points toward the center. So continuing on with the rest of the slides, what keeps you going in a circle? So what kind of force could it be? The answer is it can be any different kinds of force that you could imagine. Centripetal just means toward the center, and it refers to a direction. So if it's the Hulk, spinning a tank around, he's pulling inward on that barrel, probably also supporting it vertically too. But what gives you the circular motion is the force inward. I often show, if you YouTube an Olympic hammer thrower, I often show a video of that as well. And the last class I taught of this, the hammer thrower, her footwork was very much like the Hulk's. I originally thought the Hulk's footwork was bad, but it wasn't too terrible. Spin in a circle, and again, you have to pull inward on that. My experience is like playing around with my younger siblings growing up. You'd have to pull in on their arms to do this. Now, in a force diagram, the centripetal force means it points toward the center, but it's not some new or mysterious force. You have to give credit to whatever is doing it. So that's what this slide is about. You have to give proper credit to any forces pointing toward or away from the center of the circle. So for the Sun-Earth system, the centripetal force is gravity. For a bank to turn, the normal force partially points toward the center of the circle, not all of it, but a component of it. And there are a couple of situations with a mass on a string that we could come up with. All right. One example is if you have a mass with a string and you whirl it around your head horizontally, there's a tension force that acts as a centripetal force. But if you spin something around in a vertical circle, sometimes there are multiple forces to think about. So like at the bottom of this, the tension pulls up and gravity pulls down. And the net force toward the center is the difference between these two. And that's what that centripetal force just is, right? There could be, right, a single force that's a centripetal force, or some combination of two, or a component of a force that points toward the center. Right. I am now going to pause and reflect. Let me stop share temporarily. I'm going to pause this and confirm that there's a question on the quiz that I meant to ask you about. I'm gonna look at that while I'm gonna look at that temporarily while Nuno and Emmy play around. You don't have to watch that though. I'm gonna pause this to keep the video link down. Okay, it's a few minutes later. I confirmed that the quiz question I wanted is on there. I actually just added it. They're still playing around. All right. So the final quiz question is what I wanted to talk about next. I asked a question, right? What factors affect how hard it is to take a turn or whirl something in a circle? I'm thinking about circular motion. What factors matter? On the quiz, I asked it specifically about a turning vehicle. What determines whether you can take the turn or not? So you're supposed to list a couple of different factors, and there's, again, it's just participation points. You don't have to get anything right, but there are a bunch of common answers I get when I ask this question. Now, one of them, well, one factor is how big is the thing. So like a semi has a harder time taking turns than a car will. Now, sometimes it's the weight distribution that matters there. But if you think purely the mass of something matters for how much force you need, that's completely right. But acceleration and force are related by Newton's laws. So mass does matter, and I'm realizing I'm not sharing the right video now, so I'm just talking and you're probably watching the cats. Let me go here. Okay, this is the set of slides. This is the slide that I was going to talk about. So what factors affect how hard it is to whirl something in a circle? Many people think the mass matters, and for force, that's totally true. Other things would be like the friction on the road. So if it's raining out and the road is wet, that really matters as well. Those are force-related things, and we won't ignore them, but the most important things, and I'll make sure to notice these if any of you answer them, is that how fast you're going matters and how tight the turn is matters. If it's a really tight turn, they'll put a low speed limit on it. And I mean, speed limits matter because the faster you turn, the less safe it is. So if you're going faster, you need more force, whether it's from friction or something else, to keep you doing that. So if you know speed and tightness of the turn matter, you can calculate acceleration directly from that. Now, my whole business drawing this circle shows you the direction of the acceleration, but we need to know the size. There's a VF minus, like a change in V over change in T formula that we've used many times before, but that was one dimension and the numbers were actually changing for the speed. That same kind of trick doesn't really work here. So, right, we need some more math to do it. And it turns out the only combination that works is if you know speed and the tightness of the turn of the turning radius, this is the radius of the circle, dividing V squared over R is the only way to get something with the units of acceleration. As I've said a few times in the class before, like that kind of unit analysis, like you do meters per second all squared, and if you divide by meters once, you're left with meters per second squared. That kind of analysis doesn't prove that there isn't like a 2 or a 1/2 or something like that, but in this case, there's no funny constants in front of that. So if you know the speed and tightness of a turn, or the turning radius and the speed, you can figure out how large this acceleration is. And actually both groups, I think, who did the sample movies that you watched the last time we were together, both of them did a calculation like that. Now, they did it based on turning rate, so I have to make that connection for you too, right? Now, since F net equals ma, Newton's second law, that's the net centripetal force. If you have something moving in a circle of radius r and constant speed v, then that's the centripetal force. Now, normally, right, I would write on the board something extra. So I'll type it here. This gives you the size of the acceleration and net force needed to move in a circle at constant speed, v, and the circle is of radius r. So I mean, it's not the same as me writing on a board, but I type pretty quickly, so I can add stuff like this. Okay, so this gives you the size of the acceleration and the net force you need. So if you think larger objects take more force, that's true. Faster things take more force, that's true. Tighter circles, smaller radius, that also requires more force as well. So all of those factors matter. Okay. Now, on the homework, one of the questions refers to that gravitron ride where you're stuck to the wall because this is the amusement park ride where you're spun around and they drop the floor out, you're stuck to the wall. That one I ask a question about in terms of turning rate, so a rotation rate. And so for that, I'm inspired to bring up Calvin and Hobbes. You can read this comic here. Right, his dad is demonstrating on the record that a point on the label on the inside versus the outer edge, they make a complete circle in the same amount of time, but they both do it in the same time, the small circle and the bigger circle. So 2 points on the disk move at 2 different speeds, even though they make the same revolutions per minute. I always love this comic because if you know the strip, Calvin's dad frequently BS's the science a little bit, and he just makes up bad explanations because it's funny. But this time he's completely right, and it keeps Calvin up at night. Now, you probably know revolutions per minute as a unit of rotation rate. 33 and change is the rotation rate of most LPs, and right. The formal variable term for this is called angular velocity, and the symbol for it is this lowercase Greek omega here. Looks like a W, but it's not. So revolutions per minute is a unit of angular velocity. It's not the standard one we use in SI. What we use is radians per second, and a radian is just a different way of measuring an angle. So what a radian is an angle that cuts off part of a circle. So the arc you cut off is the same as the radius. It's about 57 degrees, and 360 degrees for a circle is the same as 2 pi of these radians. Right. Radians are used because they're dimensionless. They directly connect a circle's radius with the distance along the arc. So this red line is going to be called S on my next slide, I believe. All right. So if you remember me showing the Smash Brothers video, that was they were analyzing the rotation rate of Bowser or something like this, and some number 8 pi was given there. That's because in that clip it was 4 revolutions per second, and they converted that to 8 pi radians per second for the purposes of doing math. Now, here's another slide about radians. If an angle is given in radians and the radius of the circle is r, then the length of the arc is s. And similarly, if you go like distance divided by time to get speed, and angle divided by the time over which that changes, that's a rotation rate. That means that speed is equal to radius times rotation rate if things are written in the right units. So this is what Calvin's dad was talking about. 2 points on the disk have the same, let me highlight the right thing. 2 points on the disk have the same rotation rate, but if they're at different points, one on the edge and one not, then they have different R's and therefore different V's. So speeds and rotation rates are convertible. And you can even write out the centripetal acceleration and the centripetal force, the net centripetal force, in terms of rotation rate instead, if you want to. I hope this agrees with your idea about things like merry-go-rounds. On a merry-go-round, the hardest place to hold on is the outside. Right? It's easy to stand in the middle, you just spin in circles. But if you're on the outside, you more likely feel like you're being flung out. Now that you may have heard of that as a centrifugal force. I don't talk about or discuss centrifugal force here. Formally, that's something that appears in what's called an accelerating reference frame. An outside observer will not agree that there's a force pulling you out. So that is one way to rewrite, how big the acceleration is and how big the centripetal force is if you know rotation rate. Right. I feel like if I were giving this as a lecture, this would be about time for a break. So I might actually, just in the interest of keeping this short, cut off the slides here and then continue in a second part about how these centripetal force formulas are used in astronomy and gravity and stuff like that. So I'm going to stop the share. Check on my napping friends. Actually, no, they're one of them's up. All right, good enough. I will pause there and then talk about gravity in a little bit. And I still plan on doing some drawings and some sample problems on paper, so you can see how that's done. All right, so I will stop there, and I'll see you in another video soon.